welcome to another module in this massive open online course. So, we are looking at information theory. We have looked at Shannon's landmark result, that is the channel coding theorem, alright, which is basically gives a result for the fundamental rate at which the information can be transmitted across a channel, alright. In this module, let us start looking at a different concept, and that is of differential entropy. Okay. So, we want to start looking at a new concept, the concept of differential entropy. Okay. And this differential entropy, alright, so far we have seen, basically if you look at this, so far we have seen discrete sources with a discrete alphabet. So far with discrete alphabet, that is discrete sources. Okay. But what about a continuous source, that is a source x, okay, this is the source x, okay, and this produces a continuous signal, okay, the source x produces a continuous signal. That is a source which produces a continuous signal, which can take values, which can take continuous values, right, we can take values from a continuum. Okay. That is take values, take a continuous set. Take values from a continuous set, for instance 0 to infinity. Okay, we can have a continuous signal which can take values as against previous sources which are discrete in nature. Alright, this alphabet, the set, the source alphabet is discrete, consists of a finite number of symbols. Okay. Now, as against that, one can also consider a source which generates continuous signals, continuous or discrete continuous signals, which can take values, values from a continuous set, okay, which can take a continuous set of values. Okay. So, naturally the probability distribution is characterized by a probability density function for such sources. Okay. So, basically we are talking about the entropy, the probability distribution output belongs to a continuous set of values So, naturally the output belongs to a continuous and characterized by a it can take a continuous set of values, and this is characterized by a, the distribution is characterized, output distribution is characterized by a So far we have seen a probability mass function. Now we are going to, because the output can take from a continuous set of values, this is characterized by a probability distribution, probability density function. So this is the PDF, probability density function, or you can say this is the output PDF of source x. For instance, f of x, that is output PDF of the output generated by the source, is a probability density function. For instance, one very popular or one of the most commonly occurring random variables, right, to characterize the output of this such continuous source is the Gaussian probability density function. Okay. So, the source probability density function f of x can be Gaussian, and from the fundamental knowledge of the fundamental course on probability, we know that Gaussian can be represented as, for instance, mean mu having Gaussian. So, this shows a Gaussian random variable. This is the mean, sigma square is the variance. Okay. And the Gaussian probability density function looks as follows. Peak at the mean, let us say the mean is non-zero. Okay. So, okay, this is your fx of x, this is your x. The peak is at the mean mu. The spread of the Gaussian is proportional to its variance sigma square, and the probability density function is 1 over square root of 2 pi sigma square e raised to minus x minus mu whole square by 2 sigma square. This is the probability PDF of the Gaussian, correct? You already know this. Or you can have an exponential source, the output PDF is exponential, correct? So, this can be something like, okay, so this is the exponential PDF f of x, x equals 1 over lambda e power minus x over lambda for x greater than or equal to 0, 0 for x less than 0. So, this is your exponential. Random variable. Okay. So, the source alphabet is continuous and has an exponential probability density function. Okay. So, the output is continuous, takes values from a continuous set. Okay. It is characterized by a probability density function. Now, how do we define the differential entropy for such a source? The differential entropy, the average information, the differential entropy, let us not say average information for a particular reason. So, the differential entropy, so we are going to let me first define the differential entropy, and we are going to see something unique about this. The differential entropy of such a source is defined as h of x equals minus infinity to infinity f x of x log 2 to the base 1 over f x of x dx. Okay, so this is the difference. This is termed as differential entropy, and remember this is the definition of differential entropy. So, let me just draw this is the differential entropy for source with output PDF. And note that as against the entropy of a discrete source, this is represented using small h. Okay. Represented using h. Okay. So, this is something that you can note, okay, as against the entropy of a source with a discrete alphabet. Okay. So, this is the differential entropy, and from this you can see that it is very similar to the definition of the entropy, where we replace the probabilities, correct. In the log we have replaced the probabilities, right, probabilities by the probability density function, all right, and the summation, right, the discrete sum has been approximated, has been replaced by the integral, which you can think of as evaluating a continuous summation. Okay. So, there are two major changes, one is not two major changes. So, it is similar except for the probabilities replaced by PDF to the discrete sum has been replaced by the integral. Okay. Let us look at an example for this. To understand this better, let us look at an example. For instance, let us look at an example where I have a source, where I okay. So, this is my source, okay, source generating the symbols x, and the source x, the PDF is uniform in 0 to a. This denotes a uniform probability density function. And the uniform probability density function, remember a uniform probability density function over the range has a flat probability density function. If you look at the uniform probability density function, for instance, this is a, this is 1 over a. So, this is uniform. So, the uniform probability density function is basically given as 1 over in 0 to a is 1 over a for 0 less than equal to x less than equal to a and 0 otherwise. Okay. So, this is the probability density, this is the uniform probability density function in 0 to a, it is 1 over a in 0 to a and 0 others. And you can see this satisfies the all the properties of the probability density function, because it is non-negative, and also the area under the probability density function is 1. Okay. And now, the entropy of a source whose output is basically follows a has the uniform PDF, all right, in 0 to a, the source output is characterized by a uniform probability density function. The differential entropy, that is h of x for such a source, is given as, well, integral 0 to a f of x, that is 1 over a log to the base 2 1 over f of x a dx. This is a constant. So, 1 over a log a to the base 2 will come out 0 to a dx, which is 1 over a times a. This integral is a times a times log a to the base 2, which is log a to the base 2. So, we have evaluated the differential entropy of a simple source corresponding to the uniform probability density function, that is f of x of x Now, you will observe something interesting, that is, we have evaluated the differential entropy, which was relatively straightforward, but if you look at this differential entropy, you will notice that if A is less than 0, the differential entropy is negative, which is something that is very interesting, which did not happen with entropy. Remember, the entropy was always non-negative, that is 0 or greater than or equal, it is greater than or equal to 0. However, the differential entropy can be negative, and this is a very important difference. Okay. So, you can see that h of x can be negative. For instance, for a less than 1, log a to the base 2 is basically less than 0. This implies h x can be negative. Therefore, unlike entropy, unlike entropy, the differential entropy, and this is an important property of the differential entropy. Unlike entropy, the differential entropy can be negative. Unlike the entropy, this can be negative. So, this is an important difference one has to keep in mind while dealing with the differential entropy, that is the entropy of entropy definition for sources which can for sources with source alphabet that can take source alphabet that is not discrete, that can take a continuous set of values. Okay. So, the corresponding definition is differential entropy, and the important thing to realize is this quantity can be negative unlike entropy. Okay. We will stop with this, and we will look at other aspects in the subsequent modules.